Hello everyone, we're checking out the practice problems limiting reagents worksheet. Alright, so guys, we're taking a look at question number 8, and I know that question number 9 is like, woo mama, right? Kind of complicated, so I'm going to give you a huge step advance forward so that you can finish number 9. Now, if time allows, we'll probably look back at question number 6, but I'm just not sure if we're going to have enough time, okay? So we'll go as far as we can, alright? All right, question number 8 says you've got hydrochloric acid, so I'm just going to go ahead and write out the balanced reaction. Got some hydrochloric acid and some zinc. All right, and that reacts to make some zinc chloride and some hydrogen gas. Remember, you can't do anything without a balanced reaction, and you're so spoiled on this problem because it is balanced for you. All right, now what I like to do is put the quantities that it tells you in the problem, like right over the top of the balanced reaction. I like to do that. It just helps me. I'm a visual person. All right, so 36.5 grams of HCl, 73 grams of zinc, and then they are asking you, it says determine the reactant, determine which reactant is the limiting reactant. Find the mass of zinc chloride formed. Oh, okay, so we're going to zinc chloride in both cases. Anytime you start with two quantities, you're going to be setting up a limiting reagent problem because it's probably going to happen where one of the reactants will run out and then stop the reaction and limit the maximum amount of product you can make. So if you ever see two masses or two quantities in a problem, you're setting up two problems. Just get used to the idea. All right, part C says determine which reactant is in excess, and part D says how much excess. All right, if you can do this problem, the rest of the worksheet should be a piece of cake. Number 9 is just crazy because it's actually two reactions, and we'll look at that too, okay? All right, so we're going to set up a problem in which we will, oh, whoops, sorry, hold on. We're going to start a problem in which we are starting with the 36.5 grams of your HCl, and we're going to take this one all the way out, and it's a traditional stoichiometry problem that should end with grams of zinc chloride. Okay, and then we'll start another problem starting with the 73 grams of zinc. And we're going to take this all the way out and end on grams of zinc chloride. Now remember, you're going to get two answers. Which one's correct? Which one's the maximum you can make? The lesser amount. Okay, so let's anticipate what our steps are real quick before you dive in. What are you going to do with the grams? You're going to change those grams to what? Moles, that's right, because the heart of stoichiometry comes not from mass ratios, but from mole ratios. Once you change the mass to moles, what's the heart again? Mole to mole ratio. And where does that mole to mole ratio come from? The balanced reaction. Yeah, these ratios up here. So we'll do a mole ratio. And then at the very end, we're going to change what to grams? Because this is a mole-mole ratio, right? Yeah, you're going to change your moles into grams at the very end. Okay, what I'm going to do right now is I'm going to pause the video. All right, take a minute. You know how to do these problems. Take a minute and see how far you can take it on your own. Okay, don't continue the video until you get both answers. That way you can check your work. Okay, so this is the setup first. And those of you who are a little bit lazy about labeling, it's going to make it a little difficult for you to follow your own work. But if you can just remember to cross-cancel, okay? If you cross-cancel, it's kind of like laying down a little breadcrumb trail for you to follow. Up, for example, you've got grams HCl, you've got to cross-cancel with grams HCl. You have mole HCl, you've got to cross-cancel with mole HCl. By the way, why did I put a 2 on the HCl in that first ratio? Why is there a 2 on the bottom? Yeah, come up here. Do you see your balanced reaction? There is a coefficient of 2 in front of HCl. That's the only one up here, by the way, that has a coefficient other than 1. So that's, see how I always follow. You see mole HCl, that's mole HCl crossed off. Follow the correct substance. All right, and we're trying to get to zinc chloride, so I put the zinc chloride on the top, and there's no coefficients, that's a 1. Change that mole to mass. Okay, same process down here. All right, go ahead and take a calculator and let's see what answers you get. All right, you guys, so you have two answers. What is the maximum you can make in this problem? Yeah, it's the lesser amount, okay? So the 68.2 grams, this is the maximum amount of zinc chloride that you can make. All right, you guys, let's make sure you were listening. Which reactant is your limiting reactant, HCl or zinc? Yeah, whichever reactant produced the lesser amount. So which reactant produced the lesser amount? Yeah, this guy right here. So all of this HCl is gone. It is completely gone. There's none left over. The reaction has hit like a brick wall because when the HCl is gone, the reaction is going to stop. So guys, looking at your zinc, okay, did we use all of the zinc? No. We only used some of it. So now it's time to figure out exactly how much zinc you actually used. And some of my students get really creative, and I don't want to stifle that creativity, so there's a couple different ways that you can go about figuring out how much zinc it actually took to make this product. So some students, what they will do is they will actually take this 68.2 grams of ZnCl2, and they will do something called percent composition. You guys remember how to do that, right? What percent of zinc chloride is zinc? You can totally do it that way if you want. However, and this is my way of doing it, I do a third stoichiometry problem. It sounds like it's a lot of work, but it's not, because you already have all of your molar masses already done. So doing this last piece is actually really easy. What I'm going to do is I'm going to take the 68.2 grams of zinc chloride that I made, and I'm going to go and work a stoichiometry problem from zinc chloride to zinc. And that will tell me exactly how much zinc I used. Is that going to tell me how much is left over, though? No, it's just going to tell me how much was actually used. And by the way, when you do this last problem, you better get an answer that is less than 73, right? Right? That's right. So doing this last problem, there's a lot of safeguards that you can rely upon. First of all, you already have all your molar masses done. And second of all, you know your answer better be less than 73. Lots of cool ways to check your answers there. All right, so zinc chloride molar mass, you already did it. It's 136.4. Okay, make sure you're doing the correct mole ratio. We are going from zinc chloride to zinc, and it's 1:1. Notice how I'm just naturally filling stuff in because I'm labeling everything. You see zinc chloride. Now I'm on zinc. Already got the molar mass, 65.4 grams. All right, remember, doing this problem isn't going to tell you how much is left over. All it's doing is it's telling you how much zinc it took to make this 68.2 grams. So in order to figure out how much is excess, what do you guys think we're going to have to do? Any ideas? What do you think I'm going to have to do with this value of 32.7 grams? What does this amount mean? Yeah, this is the amount of zinc that it took to actually make your product. So this is the amount of zinc used. All right, this is the amount of zinc used. So what am I going to have to do to figure out the amount of zinc left over? Yeah, you gotta subtract. Amount of zinc left over, you have to subtract. So take the original amount that was available to you, which is 73 grams. This is the original amount that there was available. And notice your answer, sure enough, it is less than 73, thank goodness. So 73 minus 32.7. I get 40.3 grams of zinc left over. Do you guys agree? Nice. All right. So there's question, what was this, question 8? All right, very good. Time to look at question number 9, the not so friendly problem. All right, here we go. The trick on question 9 is that technically what you have is you have two reactions occurring kind of simultaneously. Let me see if I can piece this together. Your first reaction looks like this. P4 plus O2 gives you P4O6. There's your first reaction. Is this reaction balanced? Yes or no? Remember, you can't do anything without balanced reactions. Is it balanced? No. On the left, you only have 2 oxygens, but on the right, you have 6. Okay, the P's are balanced. That's fine. All right, so I'm going to put a 3 right here. Okay, there's your first reaction. But then they start talking about this other reaction. And the other reaction looks like this. It takes P4O6, which, by the way, that is the product of the first problem. You guys see that? P4O6. And it reacts with oxygen again. But this time, it's going to make P4O10. Interesting. Is that second reaction, is that balanced? No. So be careful here. Let's see. What is 6 plus 2? I'm looking at my oxygens. What's 6 plus 2? That's 8. How many oxygens you got here? It's 10. Oh, okay. So it's not balanced. How do you balance that out? Alright, so to balance this guy out, you know, you've already got 6 hanging out right here. So if you've got 6, 6 plus what will give you 10? 4, right? Yeah, so I'm going to change this dude right here to 4 oxygens just by placing a little coefficient right there. Alright, so look back at the original problem and let's see if we can figure this guy out. In the original problem, they start you off with a certain amount of P4 and oxygen. So this is actually a fairly common type of reaction where you have some kind of, you know, oxidation going on. Remember how we've talked a little bit about how when something combines with oxygen, we call it oxidation or rusting, right? Usually happens a lot with metals, but in this case we've got some phosphorus sitting around. All right, so here's the dealio. What you have is 5.2 grams of P4 combining with 5.0 grams of O2 in that first reaction. And they are just basically saying, hey, what is the amount of P4O6 that you can make? Because guess what? However much P4O6 you make, this quantity, whatever you get here, is going to be the starting amount in your second problem right here. Do you see that? And then what you're hoping for is that you have enough oxygen left over from the first reaction to actually continue into the second reaction. You're hoping that you did not use all of this oxygen. You're hoping that maybe there might be a little bit left over. And if there is some left over, guess what you're going to do with that amount? Plug it in right here. And then you'll have the starting amount for your oxygen in the second reaction. Alright guys, does that logically make sense to you? Brain check. Check your brain. Did that compute? Alright. So what we're going to do is we're first going to start by taking the 5.2 grams of your P4. And what am I going to take this to? What am I going to end on? What do you want me to end with? Yeah, the P4O6. So I'm going to end on grams P4O6. You see how you have 2 quantities, right? You've got some oxygen, you've got some P4. So guys, if you have 2 quantities, that means you have 2 things to set up. Now I'm going to take that 5 grams of O2 and I'll do another reaction down here and I'll end in the same spot. Grams P4O6. So doing a traditional stoichiometry problem, let's figure out how much P4O6 we can make. Pause the video and try this for yourself. Alright, so you have 2 different answers, and the lesser amount is the maximum amount of P4O6 that we can make. So, looks like we were able to make 9.2 grams of P4O6. So like on the original reaction, the maximum amount of this that we can make was 9.2 grams. I'm going to take that quantity and move it over into that second reaction. So that's the amount of P4O6 that we would have inside of the container. So guys, whichever reactant produced the lesser amount, that's your limiting reagent, right? So you guys see how, look over here. The P4 produced the lesser amount. That means all of the P4 is gone. This is all gone, destroyed. Next question. Do we have enough oxygen left over to start the second problem? Is there any oxygen left over? Did we use all of the 5 grams? We didn't use all of the 5 grams. So what is our next logical step? Because in order to do this, don't we kind of need to know how much oxygen is available to us? So what are we going to do? Yes, we're going to do another problem, or you can do percent composition if you like doing that. Let's do another problem that takes us from the 9.2 grams that we made of the P4O6. Let's figure out how much oxygen it took to make that. Because we didn't use all of the 5 grams, we only used some of it. All right, so let's start another stoichiometry problem, or maybe doing percent composition. Let's figure out how much oxygen it took to make that 9.2 grams. So start a problem starting with the 9.2 grams and work your way to oxygen. Let's figure out how much we use, and you better get a number that's less than 5. All right, take a minute, pause the video again, try it for yourself. Alrighty, so on the last reaction, it looks like you only used 4 grams of that oxygen, and you'll notice that that value is less than 5. Thank goodness, that's what we were hoping for. All right, so then you take the amount that was given to you, subtract the amount that was used, and you have 1 gram of oxygen in excess. So now, in the second reaction, we now know that we had 1.0 grams of oxygen that was in excess, right? Left over so that we can start that second reaction. Hey guys, guess what? You have 2 quantities, and you have a different chemical reaction. How are you going to figure out the maximum amount of P4O10 that you can make? 2 additional problems. You feel me? You have 2 quantities. One of them should start with the 9.2 grams of P4O6, and the other one should start with the 1.0 grams of O2. Right? Does that help you a lot? All right. I will give you the answer in just a minute. Pause the video one more time, and let's just see if we can build some confidence. Try it for yourself. All right, so these are the 2 problems that you should have set up, and the lesser amount is the maximum you can make. Check your mole ratios this time. Remember, we're working on the second reaction, not the first one anymore. So down here, your oxygen needs to be 2 moles, not the one from the previous reaction. The molar mass of P4O10, just make sure that that's correct. And you should get 2 answers, and the lesser amount is the maximum amount you can make. All right, so the P4O10 quantity should be 4.4 grams. By the way, in the second problem, who's your limiting reagent? Who ran out on us? Yeah, your oxygen. Your oxygen is completely gone. This 1 gram of oxygen was completely burned up. Let's see. There is now technically 4.4 grams of P4O10. Did we use all of the P4O6? No, but did we use some of it? Yeah. So what you could do is technically to figure out what is left over in the reaction left over in the reaction container, you pretty much know that all of the P4 is gone, all of the oxygen is gone. You made P4O10, you made 4.4 grams of it, and there's a little bit of P4O6 left, just a little bit. Okay, and you can actually, if you wanted to, do the math for that one. I'm not sure if it asks you. What mass of excess reactant is left in the reaction container? Oh, guess what? You guys actually have to figure that out. How much P4O6 is left over? Because you didn't use all of it. So what would you get? What's your strategy? What would you do? Yep, you would actually have to start with your 4.4 grams of P4O10 and then figure out how much P4O6 it took to make that 4.4 grams. Because you didn't use all of those 9.2 grams, you only used some of it. Pretty intense problem, huh, guys? All right. Thinking creatively, though, is essential. Problem solving, right? Solving the puzzle, solving the problem. All right, you guys, I hope this video helped, and if you have any other questions, you can always email me. This assignment right here, let's see, what day is it today? Today's Tuesday. This assignment is technically going to be due on Thursday. Anybody who does have it done at this time can turn it in, but we'll collect it on Thursday, okay? All right, then what I'm going to do is I'm going to actually move on to a lecture. All right, so you guys can tuck this away if you want. This is the lecture that we're going to be looking at now. Reactions in aqueous solutions. So get out your notes. Here we go. Let's see. Alrighty then. Okay, so a lot of chemical reactions occur in water, and you know, your planet Earth, is mostly water and is covered in water, and so you know, you got to think of the Earth as being like a giant chemical factory. We have a lot of different chemical reactions that occur, you know, in the presence of water. Water is essential to life, right? Most chemical reactions occur in water, including your body. Your body is also a giant chemical factory, right? Lots of chemical reactions that occur in water. So obviously this is an important essential piece in honors chemistry for you guys to understand. And a lot of this is going to look really, really familiar to you. Okay? So, for example, do you guys remember seeing this picture before? I know you've seen it before. What happens to ionic compounds when they dissolve in water? Yeah, they separate. The cation and the anion separate. And in this particular picture, and this is one of many, there's a few pictures I'm going to show you guys here. In this particular picture, you see the anion, the negative ion here, and it's surrounded in water. What part of water is touching that anion? What part of the water is touching it? The hydrogen. And I think we talked a little bit about this before. Water is polar. It has a positive end and a negative end. Which end is your hydrogen? Positive or negative? It is slightly positive. You guys remember how, like, if we stick hydrogen on an acid, the hydrogen has a +1 charge, right? All right, so these waters that are surrounded by that anion right there, you'll notice that the hydrogens are pointed towards it. And you've drawn this picture before. And in the picture, you see the word down at the very bottom. It says a hydrated ion. You know what hydration is, right? Do you guys remember hydrated ionic compounds? We did a whole lab to dehydrate those compounds. Remember that? So a hydrated ion is an ion that has water sticking to it. Make sense? This is what happens to ionic compounds when they dissolve. But is this true for covalent? Do covalent compounds break apart into different atoms? No. So in this particular picture, what you're looking at is a whole bunch of sugar molecules. This is a sugar crystal over on the left-hand side of the screen. That's a sugar crystal. And you'll notice that when the sugar, you know, dissolves, yeah, the water kind of surrounds it a little bit, but not in the same way. And notice that the sugar molecule stays intact. The biggest thing for you guys to remember is that water cannot split apart covalent bonds. Water can only split apart ionic bonds. Can you guys try to remember that? We've talked about this before. All right, here's another picture of the same phenomenon, just a nicer diagram. I like to show students more than one model of something just so that you can, you know, see it a couple different ways. All right, so in this particular picture, same thing. We have an ionic compound. This is a sodium ion here on top. And sodium ions, you know metals. Metals are a bunch of losers. They like to lose electrons and become positively charged. So up at the top, you've got a sodium ion surrounded, and you notice that the water, what part of water is sticking towards it this time? Oxygen. And we know that oxygen is -2 charge, right? It's kind of negative. All right, so the negative part of water is sticking its butt out towards that sodium, and then the opposite is true for the chlorine. The hydrogen is sticking towards it, and you've seen that picture before, correct? All right, this is the process of hydration of an ionic compound. Okay, this is new vocabulary for you. We've looked at so many different types of chemical reactions, but now what we're going to do is we're going to look at ionic equations. All right, ionic equations are specific to ions in water. Oh, why are we looking at this? Well, because most chemical reactions occur in water. So it's really important to understand the phenomenon that happens between ions, ionic compounds. When they meet each other in solution, that's when the magic happens, baby. That's when you get some really spectacular chemical reactions. Okay, so I'm going to show you an example. I want you to make sure that you write down the example of this reaction here. So you've got some silver nitrate, that's AgNO3, silver nitrate. What does AQ mean? You've seen a few of these symbols before. What's AQ mean? Aqueous, soluble, able to dissolve, all of that stuff. Good job. Able to dissolve. Well, sugar is able to dissolve, right? So sometimes what we'll do is we'll actually, because the sugar doesn't fall apart, we'll actually keep the sugar written in there as like AQ, but you have to understand that sugar is covalent. It technically is able to dissolve in water, right? We always dissolve sugar in water. We can all do that, right? But the sugar actually doesn't disassociate in the same way that an ionic compound does. So when you have an ionic compound, and in this case, you guys are looking at, let me see, I hope yellow shows up good. Tell me if yellow is bad or good. Is this good? Can you see it okay? All right. So when you have silver nitrate, AgNO3, and this guy is aqueous, and no, I'm not drawing like that. That's the pen doing that for me. It looks archaic. I'm so sorry. My handwriting is not that bad. All right, when this guy dissolves, because you have an ionic bond between the cation and the anion and anion are going to split apart. So when this guy dissolves in water, you will be able to create some silver ions. Do you guys remember the charge of silver? Some of you guys might have that memorized. Do you guys remember? It's an ion, so ions have charges. And it's actually a +1. Okay, and this guy's going to be dissolved in water, and that's one of the ions you're going to get. Here's the question. You guys see the NO3? It is technically a polyatomic ion. Do you know what kind of bond holds together polyatomic ions? All polyatomic ions, they are held together with covalent bonds. Covalent bonds. Can water break apart covalent bonds? No. So up here, this nitrate, the NO3, is going to be held together. It stays intact. And yes, nitrate has a -1 charge. So when silver nitrate dissolves in water, it's going to make 1 silver and 1 nitrate. And the nitrate is not going to decompose into nitrogen and oxygen. All right. So here's something kind of cool. New vocabulary, write this down. Complete or total ionic equation. This is an ionic equation that shows you each and every ion that is involved in the chemical reaction. So every time you see an AQ, look what I did. Make sure you're taking really good notes. Be meticulous. Write out every single charge that you see or don't see. Make sure you write out every little AQ that you see and every little solid. You'll notice that the only things that got torn apart were the things that said aqueous and ionic. They have to be ionic. Ionic and aqueous, ionic and aqueous. On the product though, do you guys see how we have the AgCl and it's still intact and stuck together? Why didn't I break down the AgCl, the silver chloride, on the product side? Why isn't it broken down? Because it's insoluble. It is a solid. Is it able to dissolve in water? No, if it's able to dissolve in water, we should be splitting it up as long as it's ionic. All right, what you're looking at right here is something called the total ionic equation. It shows every single ion and where it is and what's going on. But we can further simplify that equation. And the way that we do that is we have to identify these things called spectator ions. Pretend like you're a spectator at a sporting event. If you're a spectator at a sporting event, you are just there to watch, but you don't actually participate in the actual sporting event. So looking at this reaction, I want you to take a look at the silver right here. Okay, silver started off with an ion being dissolved in water. Here's the arrow. Let's try to find where the silver went on the product side. So as you can see, silver is now connected into a compound. You see how it's like in a compound now? So it looks like silver actually changed from the reactants to the products. Check out this ion right here. This is your nitrate ion right here. Okay, you notice that I have it highlighted. He is one of the spectator ions because on the reactant side he started off as an ion dissolved in water, and then on the product side here he is again, and he's still an ion dissolved in water. You see how the state of matter, the AQ didn't change. He's AQ on one side, AQ on the other side. So he's still an ion dissolved in water. He didn't really do anything. He didn't change. Same with the sodium. You'll see sodium is highlighted. He is another one of your spectator ions because in the reactant side and the product side, he is an ion still dissolved in water. Now check out chlorine. On the reactant side, chlorine is an ion dissolved in water. And where did chlorine go? What happened to him? Well, he became part of this compound with silver chloride. So he underwent a change. Therefore, he is not a spectator ion. So right now, the spectator ions are highlighted in orange. The spectator ions are nitrate and sodium. So finally, if you get rid of the spectator ions, you are left now with something called the net ionic equation. That's a vocabulary word, so it's important. A net ionic equation is an equation that only shows the ions that actually changed in the reaction. So the only ions that actually participated in the reaction were that silver and chlorine to make some silver chloride. Okay? Now, one of the things that you do need to be aware of is that when you hit the net ionic equation, yeah, you have to make sure that your atoms are balanced, right? Because there's this thing called the law of conservation of mass. Yeah, I know you guys know what that is. So the law of conservation of mass says that atoms cannot be created nor destroyed in any chemical reaction. But did you know that technically we also have to make sure that the charges are balanced in a chemical reaction? So we have this equation, this net ionic equation. We need to make sure that all of the charges are also balanced. So starting on the left side with the silver, your silver over here on the left side has a +1 charge right here. I'm so sorry, my pen doesn't want to work with me. The chlorine over on this side is a -1. So you have a +1 and a negative. What does a +1 and -1 give you? Well, they cancel each other out, right? And so it's neutral. So on the left side, you have a +1, -1, and that equals together, if you combine them, that gives you an overall net charge of 0. On the right side, you have this compound. And, you know, when you make a compound, you have to throw those ions together, and I get that part. But once those ions are thrown together, don't I always tell you to erase the charges? Compounds are not supposed to have any charges in there. So compounds have no charge. Therefore, the left side has no charge, right? Because the positive and negative cancel. And the right side, that compound, they don't have, that silver chloride doesn't have any charge either. So technically what you have is a balanced charge and balanced atoms. Let's try something a little bit different. Let's try a single replacement reaction. So first things first, what you have to do is predict your products. So take a minute, predict your products real quick before we proceed. So you should be asking yourself on a single replacement reaction, how do they work? Well, you have to check on the metal reactivity series. And in order for the lone metal, okay, to be able to cut in, it needs to be higher in reactivity than the other metal that is sitting here on the compound. So you want to see sodium higher in reactivity than magnesium. If sodium is powerful enough, it can karate chop the magnesium off, all right, and get the magnesium to be alone and kicked off and all by himself. All right, so here's your magnesium all by himself. And now the sodium has stolen the place of magnesium because he's higher in reactivity. And what it is, I combined the sodium here with that chlorine, and what you have to do is definitely check those charges. So sodium is +1, chlorine is -1, so I'm able to combine those nicely, like 1 sodium for 1 chlorine. And you'll also notice that in here, what I did, and you usually don't have to do this, but now I'm asking you guys to do this. You're now going to have to label the state of matter of your products in a single replacement reaction. So if the lone metal is all by himself, like magnesium, you see in the product magnesium, you'll notice that a single magnesium sitting all by himself in lone metal, I labeled him as solid, and that's true. Like if you have just a solid sitting by himself, he's going to be in the solid state of matter. And then the compound, you have an ionic compound, sodium chloride. what you're going to do is you're going to have to check the solubility of sodium chloride to make sure that it is able to dissolve in water. Alright, so everything's looking good here except for we didn't really balance the reaction or anything like that. So you would want to pause here and balance the reaction before we move further. Alright, so I've got everything all balanced. I had to figure out what the state of matter of my products were. And then what we're going to do now is we're going to break it down into the total ionic equation, just like we did with the double replacement. So the trick here, and this is kind of confusing for some of my students, the trick here is that when you have like a compound, for example, magnesium chloride, you guys, if you notice, magnesium has a positive 2 charge. You can look that up though, right? The magnesium ion has a positive 2 charge. And the chloride ion has a negative 1 charge. So when you make magnesium chloride, you need 1 magnesium and 2 chloride ions. So if you need to break this compound apart, you guys see how it's labeled AQ? And we're supposed to break that apart and show how the ions are able to separate and swim around in the water. You'll notice that I'm only, when I split it down, I'm only using 1 magnesium, right? And to show, if I needed more to show more than 1 magnesium ion, I'd have to use a coefficient in the front. But since I only needed 1 magnesium, there's no coefficient in the front. Now you guys see how there's a subscript of 2 on the chlorine? That's because when we made the compound, we had to use 2 chlorine ions because it's only a negative 1 charge, right? Watch what happened here. You see that subscript? That subscript showed 2 chloride ions, right? But if I want to show more than 1 ion in the net ionic equation, I have to use a coefficient, a big number in the front. So that explains why you see the 2 in front of the chloride. Alright, where I drew the arrow there. Alright, but I also want to draw your attention to the fact that over on the product side, you're also seeing the number 2 coefficient in front of the NaCl. Look at how that is expressed in your total ionic equation. Technically what we have here with the 2 coefficient in the front is you have 2 sodiums, but you also have 2 chlorines, right? 2 chloride ions. So down here, you're going to notice that I showed, if I ever have to show more than 1 ion in either a total ionic or net ionic equation, you're going to see coefficients in front of the ions to indicate that I have more than 1 of them, okay? So even if, like, for example, in this one, you know, with the magnesium chloride, even if you see a subscript of 2 to indicate that there's 2 chlorine ions, you're going to see that in a total and net ionic equation. You'll see those ions. If you need more than 1 of those ions, you're going to see them as coefficients. That's a really important concept, and many students get that really confused, okay? So now that we have our total ionic equation, we're going to do the same thing we had to do last time, and that is identify your spectator ion. So the spectator ion, in this case, the chloride, or the chlorine, did not change from the reactant side to the product side. You'll notice, though, that the sodium started off as a solid and then ended in an aqueous solution, right? So that guy changed. The magnesium started as aqueous and then ended as a solid. All right, so that definitely changed too. But the chlorine is aqueous with the charges still dissolved in water on both sides of the equation. So what I like to do, and I'll allow you guys to do this on like your worksheets, all you have to do is just cross off your spectator ions. You know, literally put a cross through them, and you won't have to do what I did, which is rewrite the equation down below. So if you just cross off your spectators, then you're done. Alright, you guys, that's pretty much everything I wanted to show you, so I hope that helps you to get started on the front page of the single and double replacement reaction worksheet that I handed out to you guys in class. You probably won't be able to do the second half of that, which is on the back side, because it's going to ask you guys to do something called the oxidation and reduction half reactions, and I haven't shown you that yet. But the PowerPoint's posted. If you want to check out those notes in advance, please do so. I would encourage you guys to do so. Alright, you guys, peace out. I hope you have a great day.